Okay, so I hope I am audible and my screen is visible to you. So let's start. This is our tutorial 6 tutorial sessions, and uh, in this tutorial session, um, we'll mainly discuss um, some characteristics polynomials, minimal polynomials of a matrix, uh, and of or a linear operator on a finite dimensional vector space, and some characteristic polynomials of the linear operator on an invariant subspaces. So let's start. Just 1 second. So this is tutorial 6. Advanced linear algebra, NOC 25 mm. I think this is NOC 25 MA 03, and today is 4th March. Just a minute. So I'll first discuss, just recall some I'll just discuss I'll just recall something related to characteristics polynomial first. Okay. um, okay, I hope my voice is audible. I think I'm audible to you, and my screen is clear too. Please confirm in message section if you are not able to.
Yes, Milan. Yes, sir. Your voice is audible
Yeah,
and your screen is visible to you.
yeah, thank you for confirming. Okay, so let's take a let A be a square matrix. Let A um, be an square matrix over a field F, and for example F, for our case F will be either complex number or real number, and most of the cases we will have this, or we may have field can be rational number as well, but for simplicity we can take field complex or rational, and complex or real, and let A be a matrix and let A equals to Aij. This way, this is an n-cross-n matrix. Then we know that we can give the linear operator. A linear operator can be given corresponding to A by this T from, let's take A is a matrix from, so this will be from F n to F n, and given by this way T x is equals to Ax for all x belongs to Fn, and then the matrix representation of T with respect to the standard order basis of Fn will be A. That is we already discussed. So now we have already discussed that let lambda belongs to the field F is said to be characteristics value or eigenvalue if there exists a vector x which is non-zero and in Fn such that t x is equals to lambda x, or equivalently ax is equals to lambda x, that is a minus lambda identity matrix, this is identity matrix, a is equals to 0, that is, or you can write if and only, that is a minus lambda in matrix is singular or not 1 1. So in that case, that case we can get determinant of a minus lambda in is equals to 0. So this is the characteristics polynomials for a linear operator t, for which the matrix representation of is a, and or as well as you can say the characteristics, this is the characteristics polynomial for the matrix a. And we have discussed that if two matrices are similar, so in that case the characteristics polynomial is also similar, that is by this way. Let's take B is the matrix which is similar to A for some invertible n by n matrix P, then then determinant of B minus lambda in is equals to, that is equals to determinant of 1 P inverse AP minus lambda in, and that one can write that the determinant of A minus lambda in. So that's why the characteristics polynomial for the similar matrices are same. So and also we have discussed that the for a linear operator T, the matrix representations corresponding to different order bases are similar to each other. So therefore the characteristics polynomial is fixed for a characteristics polynomial is fixed for a linear operator T on a finite dimensional vector space V. Okay, now what one can see here is that note that one point here, note that determinant of A minus lambda in is a polynomial of degree, also monic polynomial. This is monic, means the polynomial with the coefficient of the highest degree term is highest degree highest degree of the variable is 1. So monic polynomial, okay, I'll not write this one, when I'll discuss something that I'll write. Let determinant of determinant of A minus lambda in is a polynomial of degree n. Okay, and also we know that the determinant is, this is something like a lambda to the power n minus trace of the matrix A. These facts will be useful, but I'll not prove how this will go. Determinant of the matrix A, and also it is clear that the similar matrices has the same determinant, so therefore this is also does not affecting for linear, this is also does not affecting the linear operator T. So this all thing will be same for all things will be same for linear operator on a finite dimensional vector space V. Okay, so now this fact is there. So now I'll go to something called minimal polynomial, and so how we start it, let's take it some section type of things, minimal polynomial. So before that, let's start something. As we know that, let V be a finite dimensional vector space over a field F, and dimension of V is equals to n. Then LV, that is the space of all n by n matrices, space of all linear operators on V is of dimension n square, right? So then let T be a linear operator from V to V, be a linear operator. Then T is in this LVB, space of all linear operators on a vector space vector space B, and this will form a vector space, that's why it is called space, and it has dimension n square. Then clearly, then identity T square all the way it will go T n square contains this set, contains n square plus 1 number of element of LVB. This set is linearly dependent in LVB, because V is of finite dimensional of dimension n, and the LVB is also a vector space over the same field F with the dimension n square, as this set contains n square plus one number of elements. So therefore this set will be linearly dependent. That is, therefore there exists constant C0, C1 all the way Cn square in the field F, such that C0 plus C0 identity plus C1t plus C2t square all the way Cn square Tn square is equals to 0, such that okay, not all of them 0, that I need to therefore there exists C1 C1 C0 C1 Cn square, not all of them are 0, such that this will happen. Therefore there exists a polynomial, therefore the polynomial pt is equals to 0, where px is equals to given by this way c0 plus c1x plus all the way cn x n square, cn square x n square. Okay, so for this polynomial this is becoming 0. So now, so therefore what we are getting, that for every linear operator on a finite dimensional vector space V, the finite dimensional vector space V, there exists a polynomial for which pt is equals to 0. And how this pt is defined? Pt is defined where pt is defined this way: c0 identity plus c1 t plus all the way cn square t to the power n square. Here I will replace x by t and constant term by identity, constant 1 by identity, and constant term will be replaced by c0 identity there. Okay, so this is the thing. So now what we will just try to find, let's take the set of, so we are getting a polynomial p which this fact is called t is annihilated by the polynomial p. This fact is called t is annihilated by the polynomial p. So this fact is called t is annihilated by the polynomial p. Therefore what we are seeing that if we consider the set, consider the set of all polynomials in the set of all polynomial f is in the, let's take p is the script p is the set of all polynomials, such that f of t is equals to 0. Okay, this set consider the set this, where p script p is the set of, is the space of all polynomials. Okay, space of all polynomials over the field f, polynomials over the field f. That means the coefficients or entries of the polynomial will come from coefficients of the polynomial will come from the field f. Then and this is a subset of the space of all polynomials, and this is known that p is a PID, principal. This fact don't be confused with all this fact, because this this fact just you can forget also, don't worry. So known that this p is a it is known that the p is a, so let's write it is known that p is a principal ideal domain, or called PID. So what is the principal ideal domain or PID actually do here? Actually, for a principal ideal domain, if we consider a ideal of that set, then that will have a generating element. So that's why there will exist, and also, yeah, important thing is that this is non-empty. Okay, so let's write it here. So note that this ideal f t equals to 0 forms a ideal which is non-empty. Why it is non-empty? Because non-empty, because just few minutes ago we have talked about that for a linear operator T on a finite dimensional vector space V, one can consider a polynomial P for which Pt equals to 0. So therefore this set is non-empty, this is a non-empty, and that will form a ideal in the space of all polynomials over the field F, and so therefore there will exist a minimal generator. So it's better to ask the question some different way. So what we are seeing here is that P is a polynomial for which so P is a polynomial for which here we are getting that Pt equals to 0. So one may ask, does there exist, so one may ask the question. So better to it should be better when if I just ask these questions here. So let's do it. Okay, so okay. Just 1 minute. Yeah. So one may ask questions. So we are seeing that therefore there exists a polynomial. So for therefore for any linear operator T on a finite dimensional vector space V over F, there exists a polynomial P such that Pt is equals to 0, or there exists annihilating polynomial. So 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 one can note that one can note that for any polynomial f which is given by this way p dot g, where the multiplication is pointwise, that means p dot g at x is equals to px and gx, where for in so I'll not write this one, where okay, let me write, still it is right, p dot g at the point x is equals to px and gx. Okay, so for so note that what we are getting, that there is a polynomial p for which pt is equals to 0. So now one can consider the polynomial f equals to p dot g, where g is also a polynomial, g is a polynomial of any degree. Okay, then f of t is equals to p of t g of t, that is equals to 0. So there, what we are getting here is that, so for a polynomial, if we know that there exists a polynomial p for which pt equals to 0, so one can construct a plenty of polynomials f such that ft is equals to 0. So one may ask, the question is that, so what is the minimal polynomial or minimum degree polynomial for which pt equals to 0. So therefore one may ask, what is the minimum, in some sense, minimum polynomial p for which pt equals to 0 for a given linear operator T on a finite dimensional vector space V. Okay, so this is the questions. So now to answer these questions, let's consider all the polynomials f for which ft equals to 0, and we are saying that this will form a ideal, and all those, forget about all those things, and this will be non-empty. So therefore there should exist a polynomial which will generate this full ideal. How, what just I mean here is that, so therefore there exists a polynomial, what index I should use, what symbol I should use, polynomial p belongs to space of all polynomials such that ft equals to 0, space of all polynomials such that ft equals to 0. Okay, there exists a polynomial p such that p generator. So how one can write, so let's take c of not like this, so ideal generated by this, so that will be ideal generated means left multiplication by elements of the space p, and by addition all these things will be there. So this will be equals to f belongs to p such that ft equals to 0, and this is the called ideal generated by P. Okay, so ideal generated by P, let's write it. This polynomial P is called minimal polynomial. Minimal polynomial of T. Okay, T is a linear operator on a finite dimensional vector space V. So therefore, and this ideal generated by P means that every polynomial, if I take any element here, let's take any element from here, G from the set F, let's take, I mean, so one can write, I just write it, for any element G belongs to this set, F belongs to P such that Ft equals to 0, G is equals to something P or H for some H in the space of polynomials. Okay, so main point is that there always exists a polynomial P for which Pt equals to 0 for a linear operator T and 0, and any polynomial P. So for any polynomial which annihilates the linear operator T, that will be divisible by the polynomial, that minimal polynomial. Okay, so this is called the minimal polynomial. Therefore, P is called the minimal polynomial of T. Therefore, yeah, so I don't need to write here, then this is enough. So this is called the, therefore there exists, so one can write for a, so one can write, so theorem, I'll just write this statement. I hope this is correct. Let V be a finite dimensional vector space over a field F with dimension of V is equals to n, or I don't need dimension here, no, dimension is needed, with dimension V is equals to n. Then there exists a polynomial P of polynomial P with coefficient of highest degree term is 0, that is called monic polynomial. This type of polynomial is called monic polynomial. This type of polynomial is called monic polynomial. Okay, highest degree term, sorry, it is 1, highest degree term is 1. Okay, with such that first P T is equals to 0 as operator, linear operator. Second is that for any polynomial G, if Gt is equals to 0, then there exists a polynomial H such that G of x is equals to Px Hx, and this polynomial P is called minimal polynomial. Okay, so one more theorem I'll just write and then I'll discuss some problems. So this is now Cayley-Hamilton theorems. Okay, what it is saying that, let me just write it, the proper statement, so that I should not have make a mistake. Let T be a linear operator, T be a linear operator on a finite dimensional vector space V, if f is a characteristics, f is not a characteristic, f is the characteristic polynomial. What we have characteristics polynomial, we have said that this is actually for linear operator, take its matrix representation. Linear operator on a finite dimensional vector space, take its matrix representations and take any matrix representation and consider the determinant of a minus I n. This is called the characteristics polynomial. Okay, this is the characteristics polynomial called characteristics polynomial. Better to write fully. Characteristics polynomial of t. Okay, so so what I just want to here that let if f is the characteristics polynomial, for t, then f t equals to 0. So this is called Cayley-Hamilton polynomial. So therefore we have seen a polynomial which can be easily constructed, which annihilates any linear operator on a finite dimensional vector space V. And here we are seeing that the characteristics polynomial always annihilates a linear operator on a finite dimensional vector space V. So that's why in this way one can say that the space set of all the set of all polynomials which annihilates a linear operator is non-empty. So but yeah, so why I'm just writing the Cayley-Hamilton theorem here, because what we are seeing here is that first theorem is that for a linear operator t will have a minimal polynomial. Okay, and the second characteristic of the minimal polynomial says that if g is any polynomial for gt equals to 0, then there exists a polynomial h such that gx equals to hx equals to tx. Therefore one can say that minimal polynomial p will divide, or so therefore or one can write this way, therefore f of x is equals to p of x and h of x for some polynomial h. So in general we will denote f as the characteristics polynomial and p as the minimal polynomial. And now another theorem I will write, that is that let t be a linear operator. This theorem I will not prove, but this to have the relations between the characteristics polynomial and the minimal polynomial, we have written this way. So now the another theorem I will write that says that let t be a linear operator on an n-dimensional vector space V, or one can consider a n by n matrix A over the field A. The characteristics polynomial and the minimal polynomial, characteristics and minimal polynomial, minimal polynomials for t have the same roots except for multiplicity. What multiplicity means here, I'm just trying to say roots except for multiplicity. That is what here what I am saying, that let's take f is the characteristic polynomial that is given by suppose x minus lambda 1 whole to the power k1 all the way, or x minus lambda 1 d1 and x minus lambda k dk, where lambda I are distinct, are all distinct if this distinct if okay, let's write here. If this, then minimal polynomial px must also have the same root. Suppose this is n1 and x minus lambda k nk, and where each ni should be greater than equals to 1. each di greater than equals to 1. So main point is that let's take f is the characteristic polynomials which is given by x minus lambda 1 whole to the power d1 x minus lambda k whole to the power dk over a field where the polynomial is completely characterized, so completely factorized. So in that on that field a fx equals to x minus lambda 1 to the power d1 and this so if this is the thing, and suppose we are assuming that the each polynomial each factor is appearing, so therefore or each di will be greater than equals to 1 and they are integer obviously. Obviously they will be integer, there is no doubt about that. So then the polynomial minimal polynomial px will be something like that, x minus lambda 1 to the power n1 x all the way up to x minus lambda k to the power nk, where each factor will appear there. Okay, so this is what. So now let's go back to some problems, and if anything needed then I will um, so let's do this problem. So here it is saying that let t be a linear operator on a space of all polynomial functions of degree less than equals to 4, defined by this way, that t of a naught some polynomial of degree 4 going to this way. One can look at the this is keeping the odd degree, mainly odd degree of the x. Okay, then which of the following statement is or are correct? So let's first consider the matrix representation. Let 1 x x square x cube and x to the power 4 be the orthonormal basis, sorry, be the basis of the be the ordered basis, not orthonormal, sorry for the term, ordered basis of the space of all polynomials of degree less than equals to 4, order basis of the space of all polynomials of degree less than equals to 4. Then note that then t of 1 is equals to 1, t of x is equals to, okay, I'll write here, t of x is equals to 0, t of x square is equals to 1, t of x cube equals to 0, t of x cube equals to 0, and t of x to the power 4 is equals to 1. So note that t of 1 is sending to 1, because then in that situation a1 a2 a3 a4 all are 0. So therefore so one can write here t of 1 is equals to 1, t of x that will go to 0, and t of x square that will go to 1, t of x cube that is go to 0, and t of x4 that will go to 1. So therefore the matrix representation of t, therefore the matrix representation of t with respect to this standard this respect to this ordered basis, this is also standard order basis of the space of all polynomials of degree less than equals to 4, but this is taken order as an order basis. Then representation of t with respect to this above, to the above ordered basis, to the above ordered basis is given by, so one can look at, one can write this 1 equals to, so this will be like, this is just, okay, sorry, I made a mistake, this will be x4 not 1, yeah, that's so. So this will be 1 0 0 0 0, this second one will be 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0. This is the matrix representation of t with respect to the respect to this order basis. This is very much clear. Okay, so okay, let's write how this is clear. So 1 can be written as 1 into plus 0 into x plus 0 into x square plus 0 into x cube plus 0 into x to the power 4. Similarly 0 can be written here 0 into 1 plus 0 into x plus all the way 0 into x to the power 4, and this can be written as 0 into 1 plus 0 into x plus 1 into x square plus 0 into x cube plus 0 into x to the power 4, and this can be written 0 into 0 all the way 0 into 1 0 into 1 0 into x plus all the way all coefficient will be 0, and this is also written as 0 into 1 plus 0 into x all the way 1 into x to the power 4, and all coefficient will be 0. Therefore the matrix is this. Okay, so now what is the questions here? Algebraic multiplicity of the eigenvalue 1, and is 3 or not, and is diagonalizable or not, and minimal polynomial is this or not, and the characteristic polynomial this or not. So let's first find the characteristic polynomials, and then 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 we'll discuss. So then let's take this is equals to a. Okay, like this. Same. Then a minus lambda I, this is 5, is equals to, this will be 1 minus lambda 0 0 0 0 minus lambda 0 0 0 0 0 1 minus lambda 0 0 0 0 0 minus lambda 0 0 0 0 0 1 minus lambda. Therefore determinant of a minus lambda I 5, this is equals to will be lambda square and 1 minus lambda to the power cube. So therefore the characteristic polynomial, okay, so one can, therefore algebraic multiplicity of the eigenvalue 1 is 3. Okay, recall that we already discussed in these facts that for a linear operator T on a finite dimensional vector space V, if the characteristic polynomial is given by this, then di is called the di is called the algebraic multiplicity corresponding to the eigenvalue lambda I, and the dimension of the space of all the eigenvectors corresponding to the space of all the not eigenvectors, dimension of the eigenspace corresponding to the eigenvalue lambda I is called the geometric multiplicity. Okay, so recall that I'll just recall that if characteristics polynomial fx is equals to x minus lambda I lambda 1 to the power d1 all the way x minus lambda k whole to the power dk, then algebraic multiplicity of lambda is equals to algebraic multiplicity of lambda is equals to di, and geometric multiplicity of lambda I is equals to all those vectors, or all those vectors in the vector space V, all those vectors in the vector space V for which t minus lambda I x is equals to 0, that is the eigenspace. This is called eigenspace. Okay, so so here the algebraic multiplicity of the eigenvalue 1 is 3, because here the degree of the here the you can look at the corresponding to the eigenvalue 1. So here where one can just, so eigenvalues of t are 0 and 1. Okay, so first option is correct, therefore algebraic multiplicity of 1 is 3. So whether t is diagonalizable or not, that is first questions, that is first thing. And the characteristics polynomial, so one can look at the characteristics polynomial. Here is the characteristics polynomial is x square 1 minus x cube, or one can write it as x, so better to write this way, x minus 1 cube x square. Okay, so therefore the last option is false. So what is the minimal polynomial of t is x or x into x minus 1 square or not. Okay, just a minute. So here okay, so T will be diagonalizable if it has a basis consisting um, all eigenvectors. Okay, so just a minute. So okay, let's look at this. T is diagonalizable not later, but let's first the minimal polynomial of T is x into x minus 1 square or not. Okay, so eigenvectors corresponding to, so the eigenspace or consider A minus identity all x is equals to, x means the, here it is the vector corresponding to that corresponding to coefficients 1 x x square x to all the way up to x to the power 4. This is equals to 0. This means that a minus lambda, a minus 1 is, let lambda equals to 1 eigenvalue. So in that situation it will be 0 0 0 0 5 0 0 minus 1 0 0 0 0 0 0 0 0 0 0 minus 1 0 all the way 0 0 0 whole into x1 x2 x3 x4 x5. This is equals to 0 0 0 0. So in that case one can easily solve that x2 is equals to 0 and x4 also need to be 0. Therefore um, therefore here 1 x square and x to the power, sorry, not x square, so 1 x square, this to x square x to the power 4 are eigenvector corresponding to eigen value 1. One can look at this thing also from here, because look at that, this is eigenvalue corresponding to eigenvector, this is eigenvector corresponding to eigenvalue 1, this is eigen vector corresponding to the eigenvalue 1, and this is also, and similarly this x and x cube will be eigenvectors corresponding to the eigenvalue 0. Similarly x and x cube are eigenvectors corresponding to eigenvalue 0. So corresponding to eigenvalue 0, let's write it here 0. So therefore what we are saying here is that T is diagonalizable. Therefore T has a basis. Therefore T has a ordered basis. Therefore V has ordered basis consisting all eigenvalue of T. Therefore V has a ordered basis consisting all eigenvectors of T. Therefore T is diagonalizable. So what it is saying here is that T is diagonalizable or not. So this is also false, because here it is saying that T is not diagonalizable, but we are getting that T is diagonalizable. So one can from there say that this is not minimal polynomial, but for that, I mean, that thing I think till now it is not not discussed. So let's write the minimal polynomial, whether minimal polynomial is this or not, x into x minus 1 square or not. So look at the a so if x into x square minus if x into x minus 1 square is the, so therefore b is false, option b is false. If this is minimal polynomial of the linear operator t, then the matrix by as we know that minimal polynomial is annihilates, right? That is what the minimal polynomial means. So a minus r square, this should be 0. Okay, but what a is here, so okay, I will not do this, this will not happen. Okay, check that this will not happen. Therefore therefore x into x minus 1 square is not minimal polynomial, therefore option c is false. Okay, okay, so let's go to some other problem. Okay, so what it is saying first is that let t be a linear operator on 3 dimensional vector space over the field F. Let the matrix representation of t with respect to the standard order basis F3 is given by this way. Okay, then which of the following statement is your correct? So what we know is that the if p is the characteristic minimal polynomial, then pt is equals to 0, and if f is the characteristics polynomial, then by Cayley-Hamilton theorem ft is equals to 0. So if we can find that and also we know that p is the smallest what I can say here is that, okay, so let's first find the characteristics polynomial, then we will see. Okay, so let here given a is the matrix this 1 0 2 0 0 1 0 2 minus 1. Therefore a minus lambda I is equals to 1 minus lambda 2 0 minus lambda 1 0 2 minus 1 minus lambda. So therefore determinant of a minus lambda I is equals to a minus lambda into this will be lambda into 1 plus lambda minus minus plus minus 2 minus this will be 0. So this is the characteristic polynomial. So therefore this is equals to 1 minus lambda square plus lambda minus 2. So therefore this will be lambda square plus lambda minus 2 minus lambda cube minus lambda square plus 2 lambda. So lambda square cancel out. So this will be minus lambda cube plus 3 lambda minus 2. So therefore the characteristics polynomial is, therefore the characteristics polynomial is lambda cube minus 3 lambda plus 2. Okay, this is so by Cayley-Hamiltonian theorem. So by actually for whenever the characteristics polynomials or minimal polynomial is when you are considering, so in that situation it's we should always consider the coefficient of the highest degree element is 1. Okay, okay, so by Cayley-Hamilton theorem, that t satisfies or t annihilates by the theorem if f is characteristics polynomial of t, then ft equals to 0. Therefore what we are getting, t cube minus 3t plus 2 identity is equals to 0. So one can look at this is the correct, this is correct. So now question is that whether other options are correct or not. Okay, so other options will be correct if I mean all polynomials are of degree 3. Okay, so therefore so how one can show that other option is not correct, at least whatever knowledge we have on that basis. So as we have degree 3 polynomial, so if we consider the why other option is not correct, so let's take what is the polynomial corresponding to this first one. This will be 3x minus 2 is equals to 0. This is the polynomial. So though it is x3 minus 2x square plus 3x minus 2, I think one can so okay, so what we'll get here, x square. Okay, so okay, so let's now consider. Okay, let's do in this another. Okay, consider. Okay, so let's consider the factorize this polynomial. This is equals to lambda cube minus 2 lambda minus lambda plus 2, so this will be lambda minus 2 into lambda minus 1. Therefore the from here what one can say is that lambda equals to 2 and lambda equals to 1 are eigenvalue. So if any polynomial should satisfy, any polynomial should annihilate, so that polynomial must have the factor. So therefore by above that, therefore by above theorem, if g is a polynomial such that, okay, sorry, here I have made some mistake. This is not correct, this is lambda cube is there. So okay, so factorize it. Let's factorize it first, then we'll go. Lambda cube minus 3 lambda plus 2 is equals to 0. Therefore 1 is in root, so lambda, so lambda minus 1, lambda minus 1, lambda minus 1, so lambda square lambda cube minus lambda square plus lambda square minus lambda minus 2, lambda square minus 2 lambda minus 2 lambda plus 2 equals to 0. This is equals to 0. So what we are getting here is that lambda minus 1 lambda square plus lambda minus 2, that already we have seen here. Okay, sorry, we already have this lambda square. So here we will have lambda minus 1 lambda square minus 2 lambda plus lambda minus 2 equals to 0. So what will have lambda minus 1 lambda minus 2 lambda plus 1 equals to 0. Therefore 1 minus 1 2 are eigenvalue of t. So any polynomial g which annihilates t such that that is g of t0 must have factors x minus 1, x plus 1, x plus 2. Okay, but for all other options, like a, c and d, the corresponding polynomial does not have these factors. Corresponding polynomial does not have this factor. That is this full product. So as we are seeing that this is the minimal polynomial. Main point is that this is the minimal polynomial. Why this is the minimal polynomial? Because the characteristic polynomial is this, and the minimal polynomial should have all the factors, all the all the factors corresponding to each eigenvalue. So therefore this is the only possible choice of the minimal polynomials. So for the linear operator t, so therefore any polynomial which annihilates the linear operator t must have this factor. But here every polynomial is of degree 3, so if they have these 3 factors simultaneously, so they must be coincide to this. So therefore all other options are incorrect. So doesn't have the so okay. So therefore A, C and D are false. Okay, so go to another problem. So here what is saying, let A be a 4 by 4 matrix. This is the matrix, and then which of the following statement is or correct? The characteristic polynomial of A it is asked, and so one option will be correct from here, and whether A is diagonalizable or not, and the geometric multiplicity of the eigenvalue 1. So let's consider A is equals to, let A is equals to 1 2 0 0 2 1 0 0 minus 2 2 1 2 1 minus 1 0 0. Okay, so therefore A minus lambda I, what is this? This matrix will be minus 1 minus lambda 2 0 0 2 1 minus lambda 0 0, and this will be minus 2 2 1 minus lambda 2 and 0, this is not 0, this is minus 1, this is plus 1 minus 1 0 minus lambda. This is the polynomial. So one can look at here is that we have this symmetric. So for this type of matrix, if we have this matrix, this way matrix, then determinant of this matrix is equals to determinant of A into determinant of C. This A and C must be that n by n matrix, sorry, square matrix. Okay, if we can break any matrix by this way, but in that situation we can't write determinant of A. Main point, just what I just want to say here is that if A is equals to B 0 C D, where B and D are square matrix, then determinant of A is equals to determinant of B into determinant of D. And A should be a square matrix, obviously. Starting with a square matrix, if we have this type of decomposition, then determinant of A equals to determinant of B and determinant of D. If B and D is not square matrix, then there is no concept of determinant of B and determinant of D, so there is no point to factorize this. So therefore, with using this fact, one can say that a determinant of A minus lambda I is equals to determinant of minus 1 minus lambda 2 2 1 minus lambda into determinant of 1 minus lambda 2 0 minus lambda, and that is nothing but 1 minus lambda 1 plus lambda minus 4, this into minus lambda 1 minus lambda. This is the fact. So therefore one can write this way, lambda square minus 1 minus 4, and this will be lambda square minus lambda. So this is lambda square minus 5, this is lambda square minus lambda. So therefore one can write this is as a this factorized way, and lambda minus 1 into lambda. So therefore what we are seeing here is that this is the characteristic polynomial. Therefore the characteristics polynomial of A is x cube minus 5 into x square minus x, or x cube minus 5, write x in initially, x into x minus 1. So let's see whether, sorry, this is x square, not x cube, sorry. Is this is equals to x square minus 5 x square minus x, that is equals to x square minus 5 x minus 1. So let's see which one is correct. So obviously this is correct, this is not correct. So now let's see other things are correct or not. As we have, so note that here, here 0 plus root 5 minus root 5 1 are all eigenvalue, are all eigenvalue values of the linear operator T or A matrix here A, and all, I mean, we have four eigenvalue here, and the vector space is also four dimensional, I mean, where it is defining, or a matrix is also of degree 4. So therefore one can see that corresponding to each eigenvalue or algebraic multiplicity is equals to 1, and the geometric multiplicity, algebraic multiplicity of each eigenvalue is equals to 1, and the geometric multiplicity of each eigenvalue geometric multiplicity of each eigenvalue is equals to 1. So therefore algebraic multiplicity is equal to geometric multiplicity, therefore the matrix, why geometric multiplicity 1? Algebraic multiplicity is 1 because each polynomial, each power is 1 here clearly. Okay, why geometric multiplicity 1? Because this is very trivial, because if lambda is an eigenvalue, corresponding to that eigenvalue there must exist a vector, non-zero vector. So therefore the eigenspace corresponding to each eigenvalue must have dimension at least 1. But here we know that the algebraic geometric multiplicity is always less than equals to algebraic multiplicity. So therefore the geometric multiplicity is exactly 1. Geometric multiplicity is less than equals to 1, and geometric multiplicity is at least 1. So therefore geometric multiplicity is exactly 1, and that is same with the algebraic multiplicity. So therefore as algebraic multiplicity is same with the geometric multiplicity, so therefore A is diagonalizable, because this is what we have seen in the last tutorial, that if algebraic multiplicity is equals to the geometric multiplicity, then it is 1. On other around, one can also see that we have four distinct eigenvalue. Corresponding to each eigenvalue we have eigenvectors, and also we know that the eigenvectors corresponding to distinct eigenvalue, they are linearly independent to each other. So therefore we have minimum 4 eigenvectors, and the matrix here is represents a linear operator on the 4 by 4 I mean on the space F4 or field, whatever field you are considering here. So therefore we have the basis which is consisting all eigenvectors. So in that also true. So therefore A is diagonalizable. So therefore this option is also correct. Oh sorry, then this is not correct. It is saying that A is not diagonalizable. So option C is also not correct. Then option C is not correct. Geometric multiplicity of eigenvalue 1 is 1. That is correct, because that is what we are seeing here, that corresponding to each eigenvalue the geometric multiplicity is correct. And option D is correct. Okay. So this will give another problem. So let's do some other problem. Okay, this is what we have done now. If anything needed, then I will discuss. If anything extra needed, then I will discuss. Okay, here is something extra needed, so let's first discuss that one. So okay, I think this is invariant subspace related problem. Just let me check once. So invariant, what invariant subspace? Invariant subspace, I'll just give a definition only, short quick definition. Let T from V to V be a linear operator on a vector space V. Here we are not considering V is finite dimensional or not. It is true for every vector space V. Let T be a linear operator on a vector space V over a fixed field F, for example. So now then a subspace W of V is called invariant with respect to, or we can write with respect to T if TW is subset of W. That is what so sometimes then V is called the invariant subspace corresponding to the linear operator T here, because invariance is here due to the linear operator t. Okay, so what main point here I just want to say, what interesting fact here is that for invariant subspace, uh, okay sir, example, so example, what example one can take, the zero space, consider zero, this is a vector subspace, zero space and v, the full space, are invariant subspace to corresponding to any linear operator t. Okay, but interesting fact here is that I will talk about two fact here. One is the more invariant subspaces and another is the matrix representation. So note that let V be a finite dimensional vector space of dimension v, dimension n, and W has dimension k, then this is less than equals to n automatic. Let alpha 1 all the way alpha k be an ordered basis of W, and this is alpha k plus 1. We just will extend, because this is an order basis we are saying, so we'll extend it to form a basis of v. Let this is the extension, be an ordered basis, be the order extended order basis, be the extended order basis, extended ordered basis of v. Then matrix representation of t with respect to this ordered basis is look like this way. This is the matrix representation of t with respect to the full order basis. Let's consider this is corresponding to v and this is corresponding to w. Okay, so let's write, this is the order basis, I am writing beta and this is the beta dash. Okay, so this is the beta dash, so this will be t restricted to w, because t restricted to w is defined because t always maps w, elements of w to the elements of w. So therefore, because w is a subspace, so w can be considered as a vector space, so t restriction on w it itself is a linear operator. So now t restriction on w has matrix representation corresponding to the order basis beta. Okay, so matrix will be like this way, there will be some non-zero term and there will be some non-zero term, here will be 0. Okay, main point is that whenever I will take an element from the w and map under t, and then what we will see here is that the elements of as element of w is again an element in w. So suppose taken, just main point is what so let's take x is an element in w, then by definition x can be written as ci alpha I equals to 1 to k. Now after applying tx, what I will get, that summation of t alpha I, but these all element are is in again w, so therefore this full element can be written as summation of ci dash alpha I equals to 1 to some k. So therefore all other coefficient, that I equals to k plus 1 to n of alpha I, that will be 0. So therefore this term are 0. Okay, so this thing maybe not needed today, but this is something I just want to point out. And the another thing is that, so we have seen here is that for a linear operator t, what is the trivial invariant subspace, that is zero space and the full vector space. These are called the trivial invariant subspace, called trivial invariant subspace. So now let's consider, let t and u u are two linear operator on a vector space V, any dimension over a field F, then if t and u is equals to ut, that is called the commutes, that is t and u commutes, okay, that is t and u are commutes, then null space of t that is equals to nt, range of t that is equals to rt, null space of u that is equals to nu, range space of u that is equals to ru are invariant subspace of t and u both. Sorry, I mean not that way. So one can write this way. Null space of t null space of t and range space of t. So let's say they are invariant corresponding to invariant subspace of u. So let's see how this is invariant subspace of u. So null space of t is equals to all element x belongs to vector space V such that tx is equals to 0, and range space of t is equals to all element tx, x is coming from the vector space V. So therefore let's what we want to show that a null space of t is an invariant subspace of t, u, null space of t is an invariant subspace of u, that is what I want to show. So therefore let's take u and let's take u, x is an element, let x is an element in nt, so therefore tx equals to 0, that we know. So what we want to show that we want to show that okay, so let's write fully. We want to show that nt is invariant subspace of t, sorry, u, invariant subspace of u, that is they are already invariant subspace of t, that is clear. Why they are already invariant subspace of t? I mean for a linear operator t, their null space and range space are already invariant subspace of t, because null space elements are x such that tx equals to 0. So that means any element, take any element nt, that will again be I mean what I just want to say here is that okay, so let me just write it little separately here. Note that nt and rt are invariant subspace of t, but that is also invariant subspace of u, provided the fact that ut equals to tu. That is something interesting, that is what we are trying to look at here. Why these two are invariant subspace, that is very much clear, because suppose x element from nt, then we know that tx equals to 0, so that is again element in nt, so therefore nt is invariant under the map t. And similarly, if a tx is an element in the range of t, then consider t of tx, that is again range of t. So these are already invariant subspace of corresponding to the linear operator t. So for a linear operator t, the I mean, so better to write here range of t and null space of t are invariant subspace of a linear operator t. This is true for always. Range of t and null space of t of a linear operator t is invariant subspace. So but here we are just considering something different. So we have to show that null space of T is invariant subspace of U. So enough to show that if X is in null space of T, then T of Ux is in null space of T, that is T of Ux is again null space of T. So that is T of Ux is equals to 0. But and that is clear. Why that is clear? T of Ux is equals to U of Tx, because we know the commutativity of Tu, and but X is in null space of T, that is Tx equals to 0, that is U of 0, and this is equals to 0 because U is a linear operator. Linear operator maps 0 to 0. So therefore this is done. Similarly, to show range of T is invariant enough to show, so range of T is invariant under U enough to show that for any X belongs to the vector space V, U of Tx is again range of T, but that is nothing but, so but that will directly follow, because U of Tx is equals to Tux, but this is always in vector space V, so this is in range of T always. So these two are very trivial things. Okay, so next problem is directly maybe some application of this theorem. So what it is saying that let T and U be two linear operator on a vector space V, Ut equals to Tu, Nt and Nu. Okay, similarly one can show that range of U and null space of U are invariant subspace of T, and they are already invariant subspace of U, that is, there is no doubt about that. So but all these things are happening under the condition that Ut equals to Tu. Let Nt and Nu be the null space of T and U respectively, and Rt and Ru be the range space of T and U respectively. Then which of the following statement is or are correct? So Nu is not invariant under T, that is false. Ru is not invariant under T, that is again false. Nt plus Ru is again invariant under T, that is true. And Rt and Nt are invariant under T, that is true. So let's this is problem number 5. Last two options are supposed to be correct. Yeah. So this is okay. This is clear. This is what I am saying. This is why this is happening, because suppose this is because let W1 and W2 are invariant under a linear operator T, then that is T of W1 is subset of W1, T of W2 is subset of W2, then T of W1 plus W2, 3 is linear operator, take any element from here, that is something like alpha plus beta, then T alpha is again in W1 and T beta is again in W2, because this is already what happening. So therefore T alpha 1, T W1, W2, W1 plus W2 is subset of W1 plus W2. W2. Okay, so this is also correct then. Okay, so now next question. So here question is that which of these matrices are diagonalizable over R. So what we have seen is that, okay, so which of these matrices are diagonalizable? Let's check. Here is no option, we have to check one by one. Let's take option A, that is consider A is equals to 1 1 0 0 2 0 0 0 1. So one can look at this matrix can be written is this way. Okay, so if you want can diagonalize this matrix 1 1 2, So therefore it will be diagonalizable. Recall that a matrix is diagonalizable. Why I am saying this? A matrix A is diagonalizable. A matrix A that is something like is diagonalizable if there exists a invertible matrix. There exists an invertible matrix of same order. I am not writing order. Matrix P such that P inverse AP is diagonal. So now if 1 1 0 2 is diagonalizable, so there must exist some matrix P that is in 2 by 2 order over the same field F. Hopefully this field is considering R. Yeah, so let's write it is as R, such that P is invertible. Okay, P inverse 1 1 0 2, P is a diagonal matrix. Okay, so if we have this particular fact, suppose we have this fact that this matrix is diagonalizable, so then for this matrix A one can get P dash that is equals to P 0 0, this is 2 by 2 matrix, and 1. So then P dash will be invertible. P dash inverse will be P dash inverse will be P inverse 0 0 1, and so then P dash inverse A P dash inverse will be the diagonal matrix. So this is very clear if we can. So therefore it's enough to show. So I am not writing those things. Therefore it is enough to show 1 1 0 2 is diagonalizable. But this is true because this matrix, this 2 by 2 order matrix, this 2 by 2 matrix, 2 by 2 ordered matrix has two different, or have I think have two distinct eigenvalue, distinct eigenvalue, and they are 1 and 2. So as this matrix has two distinct eigenvalue 1 and 2, so therefore this matrix is diagonalizable. Why this matrix is diagonalizable? Because it has two distinct eigenvalue. Corresponding to each eigenvalue we will have eigenvectors. Okay, so there will be two eigenvectors. So for a 2 by 2 matrix, if we have two eigenvector, two linearly independent eigenvector corresponding to different eigenvalue, so therefore that will be diagonalizable. So once this matrix is diagonalizable, the way what we have discussed few minutes ago, that then this matrix will also be diagonalizable. Therefore A is diagonalizable. So option A is correct. So let's see for option B. So option B, A is equals to 2 1 0 2 1 0 0. I think 3 is there. Yeah, 3 is there. So this is diagonalizable or not? So one can see that it has two eigenvalue, two distinct eigenvalue, that is 2 and 3. Okay, why it has two distinct eigenvalue? This is very known fact, I mean, and also clear that if we have a upper triangular matrix or lower triangular matrix, so in that situation the diagonal entries are the only eigenvalue. Okay, so therefore here 2 and 3 are the only eigenvalue. So what, and 3 has, and algebraic multiplicity, I will write in capital, algebraic multiplicity of 2 is equals to 2, and algebraic multiplicity of 3 is equals to 1. So therefore that implies geometric multiplicity of 3, that is the number of eigenvectors, sorry, that is the dimension of the eigenspace corresponding to the eigenvalue 3 is 1, because geometric multiplicity must be at least 1. Geometric multiplicity it should be at least 1, but here it should be less than equals to algebraic multiplicity, but here algebraic multiplicity is 1, so therefore geometric multiplicity is exactly 1. So if we can show that the geometric multiplicity of 2 is 2, then that matrix will be diagonalizable. If we can show that the geometric multiplicity of 2 is 1, then the matrix will not be diagonalizable, because in that situation we will not be able to have a ordered basis of the I mean R3 such that the A can be represented as a diagonal matrix. So let's consider, let A minus 2y, what it is, that will be 0 1 0 0 0 1 0 0 1. So then let x belongs to R3 such that um, a minus lambda is 2 here, a minus 2y x is equals to 0. Therefore what we are getting here is that 0 1 0 0 0 1 0 0 1, here it is x y z is equals to 0, where x is equals to this vector x y z, 3 vector I am writing. So therefore what we are getting here is that y is equals to 0 and z equals to 0. So x can take any value, therefore the eigenvector corresponding to all possible eigenvector of the eigenvalue 2 is some constant c 0 0. This is the, and c is real number and c not equals to 0, because in that situation c will be, so therefore the eigenspace, therefore the geometric multiplicity of 2 is equals to 1 4, therefore that is not equals to algebraic multiplicity of 2, therefore the given matrix is not diagonalizable. You can calculate this from many way, but this is also one way. Given matrix is not diagonalizable. Okay, so therefore option B is false. Okay, now let's go to the option C, that is also be not diagonalizable, because one know that this is something factor, that this will not be. Okay, so let's write this one. So option C, that is 1 1 0 0 1 0 0 0 2. I think I have written correctly. Okay, so this is not diagonalizable because I can value are 1 and 2. Algebraic multiplicity of 1 is equals to 2 because it has repetition 2, and algebraic multiplicity of 2 is equals to 1. So geometric multiplicity of 2 is equals to again 1. So let's take x is equals to x y z, 3 vector in R3 such that a minus identity, that is corresponding to the eigenvalue 1, x y z, that is equals to 0, and that is same with saying is that 0 1 0 0 0 0 0 0 1, this with x y z is equals to 0, that implies that y is equals to 0, z equals to 0. Therefore similarly dimension or geometric multiplicity of the eigenvalue 1 is equals to 1, because here x can take any value, so therefore the element c00, this type of element with c not equal to 0 are the eigenvectors, and this type of elements corresponding to c any real number forms the eigenspace corresponding to the eigenvalue 1. So geometric multiplicity 1, which is not equals to algebraic multiplicity, so therefore not diagonalizable. Therefore the given matrix is not diagonalizable. Okay, so option, this is also false. So similarly one can show this is also not possible, but let's try it. So that matrix was 1 0 0 minus 1 2 0 0 minus 1 2. I think this is the matrix, option D. This is the matrix 1 0 0 minus 1 2 0 1 2. Yeah, this is 1 2 whatever, but I think, okay, let me check just written correctly or not. This is option T, 1 0 0 minus 1 2 0 0 1 2. That's true. So for this matrix also the eigen value is 1 and 2. Algebraic multiplicity of 1 is equals to 1, therefore geometric multiplicity of 1 is equals to 1. Algebraic multiplicity of 2 is equal to 2. So let's check the geometric multiplicity of 2. So let xyz is equals to x is equals to x belongs to R3, be an eigenvector of 2, then a minus 2y x is equals to 0, therefore a minus 2y will be 1 0 0 minus 1 0, so this will be minus 1 0 0 1 0, this with x y z equals to 0. So this will give x is equals to 0 and y is equals to 0. Therefore the elements 0 0 z such that z belongs to R is eigenspace of 2. Therefore dimension or geometric multiplicity of 2 is equals to 1, which is not equals to algebraic multiplicity of 1. So therefore here the not equals to algebraic multiplicity 1, so therefore the given matrix is not diagonalizable. So given matrix is not diagonalizable, so therefore this option is also not correct. Okay, so one can check various way. This is also in standard way. So another way is finding minimal polynomials and characteristic polynomials. I think this is not already done, that if the minimal polynomial is completely factorized over the field where the diagonalizability is asking, so then it will be diagonalizable, and this is if and only condition. So but that is not done yet, so therefore we will not discuss this one. This is done. Okay, this is done. So this is another problem. Let's A be an 3 by 3 matrix, okay, for which a to the power n equals to identity. So it is asking the which of the following statements are is or are correct. Okay, so what is the demand in that minimal polynomial of a can be only of degree 2. Okay, minimal polynomial of a can be of only degree 3, either a equals to this and or the uncountable many a satisfying the above equation. Okay, so let's check one by one. So if we try to find what the minimal polynomial is, so 3 4 options will be clear. Okay, so given that a to the power n is equals to identity, therefore the matrix A, that is of 3 by 3 order, that is a 3 by 3 order, satisfy the polynomial equation x to the power 1 minus 8 equals to 0, but x to the power 8 minus 1 is equals to one can write x to the power 4 minus 1, x to the power 4 plus 1, that can be written x square minus 1, x square plus 1 x to the power 4 plus 1, that can be written x minus 1 x plus 1 x square plus 1 x to the power 4 plus 1. So therefore as the linear operator A or matrix A is annihilated by this polynomial, then if P is the minimal polynomial, if P is the minimal polynomial of the matrix A, then it is clear that the minimal polynomial must be less than equals to degree 3. Why? Because the matrix is of order 3, so 3 by 3, so therefore the characteristics polynomials can have maximum degree 3, and the minimal polynomial always divides characteristics polynomial, so therefore minimal polynomial degree of the minimal polynomial must be less than equals to 3, but that is not guaranteeing that that will be 3 or 2. So let's see what it is. P is the minimal polynomial of A, then P must divides the polynomial x minus 1 x plus 1 x square plus 1 x to the power plus 1. This is the complete factorization of the polynomial x to the power 8 minus 1. So and the polynomial is considering over the real field, so therefore the minimal polynomial must contains whatever factor in the minimal polynomial will have, that must contains from here. Okay, but so here it is saying that let A be any element of R3 by 3 such that A3 equals to, then which of the following statement is or correct. So minimal polynomial of A can be only of degree 2, that is false. Option A. Let's take A is equals to, minimal polynomial can have degree 2, so we have to construct a linear polynomial of degree 3, right? So let's construct linear polynomial of degree 3. Consider A is equals to 0 1 minus 1 0, and these entries are 0 0 0 0 1. So in that situation here let A equals to this, then then A minus lambda I, this will be minus lambda 1 minus 1 minus lambda 0 0 0 0. Okay, why I have taken this one, this row is not there. So this will be, I am taking 3 by 3 matrix, obviously 3 by 3 matrix 0 0 1. So then this is 0 0 minus lambda, then one can look at that determinant of A minus lambda I is equals to lambda square plus 1 into lambda minus lambda. So characteristics polynomial is equals to, therefore characteristics polynomial of A is equals to x into x square plus 1, which is also equals to the minimal polynomial. Why this is minimal polynomial? Because if we do it if we do the factorization of this polynomial, what I will get? X to the power x plus I x minus I. Okay, so better to state a theorem. So this is not theorem, this is something remark. This is very important remark. What remark this is, I just want to say here is that let A be a matrix over a field F, and F1 is a field which contains F as a subfield, then which contains F as a subfield, then characteristics polynomial, minimal polynomial, characteristics polynomial always fixed, that does not depend on the field, because that is determinant of A minus lambda. Whatever entry is in A, that does not depend. But minimal polynomial, that is something we are considering very different way. That is the smallest degree polynomial which annihilates the operator or the matrix. But here, so one may expect that if we change the matrix from real to complex, or complex to real, or real to rational, or rational to real, so whether minimal polynomial is changes or not, but that is not the case. So then minimal polynomial of A over both the field are same. Both the field F and F1 are same. Note that characteristics value may changes because for example in this particular case the characteristics polynomial is x plus x square plus 1. So if we consider 0, then x equals to 0 is an eigenvalue, that's true, and that is only real eigenvalue. But x is equals to plus minus I is also root of this solution of this equation, polynomial equation, but they are not eigenvalue over real, they are not eigenvalue when we are considering this matrix over the real field. But if we consider this as a matrix over the complex field, because that is the linear operator, right, with respect to the standard order basis, so then it has the three eigenvectors corresponding to the 0 plus minus I. Okay, so therefore main point here is that eigenvector may changes over if we change the field. Okay, but eigenvalue will minimal polynomial will not change at any cost. Okay, characteristic polynomial will obviously not change, but the minimal polynomial will also not change. So the minimal polynomial, so why I am just stating this theorem here, I just want to point out one fact here. If we consider this particular polynomial, which is characteristic polynomial, and it has only one eigenvalue over the, when it is considering as a matrix with entries from the real, and that is 0. Okay, but if we consider this is as a matrix with entries from complex numbers, and it has three eigenvalues, then they are distinct. As they are distinct, so their minimal polynomial as a matrix with entries over C will be this particular full matrix, and so therefore here we have three distinct eigenvalues, and the matrix is also of 3 by 3. Okay, so for corresponding to each eigenvalue there should exist an eigenvector, so therefore there should exist a basis over the complex field C such that the matrix is diagonalizable. Okay, so that means this is diagonalizable if we consider it as a matrix over the complex field. But the minimal polynomial is clear, that is what I just want to say, that minimal polynomial will be there because as we know that characteristic polynomial and minimal polynomial we will have same roots, so that means they should have each of the factor at least once, but here one can have at max one also. So therefore this is the minimal polynomial, because that will not change if we change the eigenvalue, sorry, if we change the field. So therefore the minimal polynomial of the matrix, minimal polynomial of the above matrix is x square plus 1, which is not of degree 2, which is not of, or one can write, and the degree of this is 3, and degree of this polynomial is 3. Okay, so therefore the first option, that the minimal polynomial of A can be only of degree 2, that is false, because I can construct a matrix A for which the minimal polynomial is will have degree 3. But why this matrix will satisfy a to the power 8 equals to identity? Because because if the matrix satisfies this condition and this is 0, I mean we are getting that A into A square plus identity, this is 0, so if whatever matrix we may multiply with this, that will be 0 again. But if we multiply B just by this matrix, B is equals to, okay, sorry, here I have to change little bit. Here x, oh no, sorry, I have made mistake here little bit. A equals to plus minus, yeah, x minus 1, so let's write it is as in I have written correctly, but here I have written incorrectly, 1 minus lambda, so this will be 1 minus x, this is lambda minus 1, or this is lambda minus 1, sorry, this is x minus 1, so this is x minus 1, Okay, so all things are correct. Okay, x minus 1, x plus I, x minus I. So in that situation everything is correct. So what we are getting here is that minimal polynomial of this matrix A is this one. So A will be like this way, a square plus identity is equals to 0. So whatever matrix I may multiply, that will be again 0. So instead of anything, if I multiply this particular thing, a plus 1, a to the power 4 plus identity, so this will be a to the power 8 minus identity. Okay, so therefore this will again be 0. So therefore this matrix, the matrix A is given here, is satisfy this above condition. So I'll write this one. Therefore for the above matrix, note that the above matrix A, for above matrix A, matrix A to the power 8 equals to identity. So first option is incorrect, that is main point. Minimal polynomial of A can be of degree 3. That is not necessarily, can be, okay, what the minimal polynomial of A can be only of degree 3, that is also not true. Consider A equals to identity, 3 by 3 order matrix. So then minimal polynomial is x equals to identity, x equals to 1. So this is the minimal polynomial. So minimal polynomial is x minus 1 basically. Okay, so this is not correct. Either a equals to identity or a equals to minus identity. So that is also not correct, because we have given a is this way. So and this also gives that option C is also not correct. Option C is also not correct. So therefore only option D it should be correct, but let's check this is correct. So there are uncountably many A satisfying the above equation. Okay, we have to construct uncountable many A which satisfy the above equation. So what we have says that we have seen that the matrix A, which is given by 0 1 minus 1 0 0 0 0 0 1, seen that this if then a to the power 8 equals to identity. Now for any invertible matrix P of degree 3, P inverse AP is will satisfy the equation, above equation x cube equals to 1. Okay, so therefore option D is correct, because we can this is true for any invertible matrix P of degree 3 by 3 order. So one can get in uncountable number of 3 by 3 order matrix P which is invertible. So therefore P inverse AP is equals to this type of matrix will be satisfy this equation. A cube equals to, I mean basically main point is that B cube equals to identity. Okay, so this will satisfy. So let's do next one. This is already done. So now what it is saying, let T be a linear operator for such that Tx equals to Ax, that here A is this. So therefore here A is the matrix representation with respect to the standard order basis of R3, that is 1 0 0 0 1 0 0 0 1. So let's W equals to span equal, it is given that span of this vector 2 1 0 transpose 3 minus 1 3 transpose, and this is, and TW denotes the restriction of T on W. So that is, it is saying that this elements, this space W is invariant with respect to T, but we will check. Then which of the following statement is or are correct? The characteristic polynomial of TW is given by this, a characteristic polynomial of t is given by this way, product of the eigenvalues of t minus sum of the eigenvalues of this, all these things is given. So let's first find what is the product of the eigenvalue, sorry, what is the eigenvalues of this matrix. Okay, so this is questions number 8, right? So here note that there is polynomials of t with respect to w. Okay, so let's take full matrix A. What it is? It is given 5 minus 6 minus 6. Okay, I'll do some different way. Okay, so here note that A is equals to given by 5 minus 6 minus 6 minus 1 4 2 3 minus 6 minus 4. So let's A into 210, A 210, that is equals to 5 minus 6 minus 6 minus 1 4 2 3 minus 6 minus 4. This is 2 1 0 1 0. So this will be first 10 minus 6, that will be 4, minus 2 plus 4, that will be 2, and another will be 6 minus 6, that will be 0. So this is equals to 2 times 2 1 0. So therefore 2 is an eigen value of A. Okay, with eigenvector, this is the 210 is the eigenvector. Okay, so similarly if I try to find A of the other vector 3 1 3 minus 1 3 3 minus 1 3, then it will be 5 minus 6 minus 6 minus 1 4 2 3 minus 6 minus 4 3 minus 1 3. This is equals to 15 plus 6 21 minus 18, that is 3, that is 3 minus 4 minus 7 3 to 8 plus 1, okay, sorry, 3 minus 7, okay, minus 1 minus 7 plus 6, and next is 9 plus 6 15 minus 12 3. So therefore 1 is an eigen value of A. Okay, that is clear. So 1 is an eigenvalue and 2 is an eigenvalue, and also here it is clear that what are the eigenvectors corresponding to each eigenvalue. And also we know that, note that if lambda 1 lambda 2 lambda 3 are eigen value of A, with repetition we are considering, that means lambda I can be equal to some lambda j with repetition we are considering. Okay, then lambda 1 plus lambda 2 plus lambda 3, that is equals to trace of the matrix A, and we know that lambda 1 lambda 2 lambda 3 is the product of the matrix A. So therefore, and this is equals to trace of the matrix A is 5 plus 4 plus minus 4, that is 5. Okay, 5. And also what we have seen is that 1 and 2 are the eigenvalue. So if lambda 1 is equals to 1, lambda 2 is equals to 2, then lambda 3 is equals to 2. So therefore 2 1 and 2 is the 1 and 2 are eigenvalues of A, and they are the only eigenvalues. And characteristics polynomial of A is equals to x minus 1 and x minus 2 square. This is the characteristic because 2 eigenvalues is repeating twice, so algebraic geometric multiplicity is 2. So therefore the characteristics polynomial for t is 6 1 2, that is false. The characteristics polynomial as a product of the eigenvalues of t minus sum of the eigenvalues of tw. Okay, so from the above what we are seeing here is that t, the matrix A, that is on 2 1 0 is again 2 1 0, and t on 3 1 minus 3, that again 3 3 minus 1 3. So therefore t restricted to w, that is on 210, that is giving 2 times 210, and t restricted to w, that is 3 minus 1 3, that is again 3 minus 1 3. So these are the two eigenvector corresponding to t restriction and w as well. Okay, so therefore the second option is says that the characteristics polynomial for tw is, this is also true I think. Okay, sum of the eigenvalues of tw. So eigenvalues of tw, therefore eigenvalues of tw is equals to 1 and 2, and so therefore here it is says that product of the eigenvalues of t minus sum of the eigenvalues of t, product of the eigenvalues 1 cross 2 cross 2, that is the eigenvalues of t, minus sum of the eigenvalues 1 plus 2, that is equals to 4 minus 3, that is equals to 4 minus, sorry, that is equals to product of the eigenvalues of t, that is 1 cross 2 cross 2, product of the sum of the eigenvalues of tw, that is 3, right? Sorry, I'm talking about sum, I'm not, 3 is 1, so this is correct. Okay, so t is diagonalizable or not, so that depends whether the geometric multiplicity of t is 2 or not. So let's take the matrix, full matrix, what it is, that is 5 minus 6 minus 6 minus 1 4 2. So let's consider let a minus 2y, what it is, this is equals to 3 minus 6 minus 6 minus 1 2 2 3 minus 6 minus 6. So a minus 2y whole x, let x is equals to x y z. Okay, whole x is equals to 0 implies that 3 minus 6 minus 6 minus 1 2 2 3 minus 6 minus 6 whole x y z is equals to 0 0 0. But note that all these three are scalar multiple of each other, so therefore what will have essentially this one, 2x 2z is equals to 0. Okay, so therefore x is equals to 2y plus 2z, so therefore eigenvector, so the basis, so 2 1 0 and 2 0 1 are linearly independent eigenvectors of t, are linearly independent eigenvectors of 2. So therefore t is diagonalizable. Okay, so t is diagonalizable, this is true because we have 3 eigenvectors, because corresponding to 3 1 minus 3, this is an eigenvector corresponding to eigenvalue 1, and these two are the eigenvectors corresponding to the so therefore geometric multiplicity of 2 is equals to 2, that is equals to algebraic multiplicity of 2, that's why it is true. And one can look at, if we restrict it to the subspace w is a subspace corresponding to the these two vector, so this is 2-dimensional subspace, so for that case we will have characteristics polynomial is also this one. So this is not characteristics polynomial because it should be x minus 1 x minus 2, so but it is written as x plus 2. Okay, so here one can say here from here is that the characteristics polynomial of t restriction to w is equals to x minus 2 x minus 1. Okay, so that implies option a is false. So So this is all. So we will not do this. I will stop here. So these two are the correct options, and the first two is false option. Product of the eigenvalues of t minus some. This is also done, and t is diagonalizable. That is also true. So we will not do again. We will not do any more questions for today. So this is all. So from the next week, we will have regular class on each Saturday from 6 p.m. to 8 p.m. So I think if anything is there, we can discuss, or otherwise we can stop in next 30 to 40 seconds. Okay, so we'll stop here. If anything, if there is nothing to ask.
Okay, thank you, sir.